Welcome dear students. Welcome to another video on transmission line theory. We are dealing with Smith charts and this is problem number 1. In this problem we are going to see a question whose difficulty level is intermediate level. And this problem is based on load impedance or input impedance, VSWR, reflection coefficient and return loss. So let's read the question out. So the question says a load impedance of 40 plus j 70 ohm terminates a 100 ohm transmission line that is 0.3 lambda long. Find the reflection coefficient at the load, the reflection coefficient at the input to the line, the input impedance, the standing wave ratio on the line and the return loss. So in this question, basically a transmission line is given, a parallel transmission line, whose characteristic impedance is Z0, which is equals to 100 ohm. And a load is attached, whose value is given as 40 plus j 70 ohm. And the length of the transmission line is given as L is equals to 0.3 lambda. And you have been asked to find the reflection coefficient at the load, the reflection coefficient at the input side, the input impedance Zin, the VSWR and the return loss. Okay, now we very well know that dealing with Smith charts requires normalized impedances. In this question, the impedance load ZL is given as absolute value. So in order to find the normalized impedance, you need to divide ZL with Z0. Okay, so let us do that first. So ZL over Z0 will be RL over Z0 plus J times XL over Z0, which will be 40 divided by 100 plus j times 70 divided by 100. That will give you a value of 0.4 plus j 0.7 ohm. So you know that these normalized impedances are written in small case letters. So we will write ZL, which is equals to RL plus JXL, and we got that value as 0.4 plus j 0.7 ohm. Alright, now we are going to plot this value in a Smith chart. Now let's go to the Smith chart first. So this is a Smith chart. In this Smith chart, if you see this horizontal line, this line indicates the real part of the impedance. So if you see here, it says resistance component R over Z0 or conductance component G over Y0. Since we are dealing with impedance, so we require R over Z0. So we have the resistance component, which is R over Z0. Okay, so what do we have? We have ZL is equals to RL plus JXL, which is equals to 0.4 plus j 0.7. So the value of RL is 0.4 and value of XL is 0.7. So in this axis, this point is the value of RL, and the constant resistance circle, whose value is 0.4 throughout that resistance, will be the circle which passes through 0.4 value at the real axis. So this circle is RL is equals to 0.4. Okay, similarly for XL is equals to 0.7. Since this is plus J, so we are going to look at the upper hemisphere of the Smith chart. Now here if you see, you have 0.7 marked over here. Therefore, this particular circle will be XL is equals to 0.7. Okay. Now when you draw both of these circles together, so I have drawn it here for you. So here this value is RL is equals to 0.4. This circle is RL is equals to 0.4 circle, and this circle is XL is equals to 0.7. So the point at which this circle meets, this point represents your load impedance, the normalized load impedance. So this value, this point ZL will be 0.4 plus J 0.7 ohm. Okay. Now once you have found this value, this point in the Smith chart, this particular point in a Smith chart, then you can find the VSWR circle and the angle of the reflection coefficient as well as the magnitude of the reflection coefficient. Now let us see how we can do that. So you have already got this point. From the center of the Smith chart, if you draw a line which meets at this point, okay, this line, then keeping this as a radius, if you draw a circle with center at this point with this as a radius, then this particular circle is called your VSWR circle. And when you drop a line from the VSWR circle to these scales, okay, let me show you here. This line is drawn straight down below and it cuts these scales. Now if you watch carefully, these scales tells you the value of VSWR, return loss, reflection coefficient, etc. So if you see this line, this particular line, on top of this line there are few numbers written. These numbers are SWR in linear scale. Similarly, below this line there are few numbers written. These numbers are SWR in dB scale. Okay, that is what is written here. dBs is SWR in dB and SWR is simply in linear scale. Okay, so you see this is cutting at somewhere 3.8. So this value VSWR is 3.8 and it's in linear scale. Okay, if you see here, it also cuts the reflection return loss in dB as somewhere near 4.8 dB. So return loss in dB is 4.8 dB, and the reflection coefficient will be mod of reflection coefficient for the load is somewhere 0.58 in linear scale. Okay, so we have found the value of reflection coefficient, magnitude at the load end. We have found the value of VSWR and we have found the value of return loss in dB. Now let us try to find out the angle of the reflection coefficient. So if you just extend this line up till here, okay, the line which starts from the center of the Smith chart, crosses the ZL point, and it extends up to this point. Then here these values are the values for the angle of the reflection coefficient. If you see, if you come to the extreme right, it says angle of reflection coefficient in degrees. Okay, so that is why this point is your angle of reflection coefficient. So let me write it for you. It says angle of reflection coefficient gamma L is equal to 103 degrees approximately. Okay, all right. So you have found out the value of gamma L, whose magnitude as well as the angle gamma L. So the magnitude was 0.58 and the angle is 103 degrees. Okay, now our next objective is to find the value of ZIN, that is the input impedance of the transmission line seen from the input end. For that, we have to first find that this line cuts at which value for this particular scale on the topmost scale. Now if you see here, if you come to the extreme left of the Smith chart, let me zoom in further. Yeah, it says wavelength toward generator, and the direction is given as the clockwise direction. So whenever you move from the load end towards the generator, you need to move in the clockwise direction in the Smith chart. That's what this scale suggests. Okay, all right. So we have found the point where this value is representing the wavelength. Its value is approximately 108 lambda. Okay, now in the question it was given that the length of the transmission line is 0.3 lambda. Now you are sitting at this point ZL, and you need to find the value of the impedance at the input end, ZIN. So from here to here you need to move a distance of 0.3 lambda. Okay, so that is what we are going to do here. So this point is 0.108 lambda. So if you just add 0.108 plus 0.3, which is 0.408 lambda. So moving in the clockwise direction, that is in this direction, and if you reach at 0.408, which is somewhere here, then you can find the value of ZIN. Okay, so for that I have already done it for you. So from this point, so this was the point of 0.108 lambda. So from this point you have moved in the clockwise direction like this, and you have moved a distance of 0.3 lambda, so that you have reached a point of 0.408 lambda. Okay, so from this point, if you draw a straight line which cuts the VSWR circle at some point and meets at the center of the Smith chart, then you can find the value of the ZIN. So the point at which it cuts the VSWR circle, that value will represent the ZIN value, that is the normalized input impedance. So the value of RIN will be, let me choose a different color. Okay, so from here, if you draw a circle, which passes through this point. Now if you check, it is somewhere it is crossing close to 0.36. So this is the value of RIN, the normalized input resistance. Similarly, if you draw the reactance circle passing through this point, that will be this curve, and this curve is saying 0.6. So the value of XIN is 0.6, and since this is in this particular plot, this curve is in the lower half of the Smith chart, so that is why it is capacitive in nature. That is why it will be minus J. All right, so this point is basically representing ZIN, which is equals to 0.36 minus J 0.6 ohm. Okay, now one last thing, that you can also find the value of the angle of the reflection coefficient from the input end. Okay, so for that will be this particular value. So that angle is angle of reflection coefficient seen at the input end, and its value is approximately minus 114 or something. So minus 114 degrees, which can also be written as in positive values as 246 degrees. So how do you get 246? You just subtract 360 minus 114, which is 246 degrees. Okay, all right. So what we have found out, let me summarize it for you. So initially we had ZL, the normalized load impedance, which was 0.4 plus J 0.7 ohm. Then we found out the value of the VSWR, which was 3.8 in linear scale, and we also found the value of the return loss in dB, which was 4.8 dB, and then we found out the value of the mod of the reflection coefficient from the load end, which was 0.58, and then we found the value of the angle of the reflection coefficient from the load end, which was 103 degrees. Therefore, using these two, you can say that the load reflection coefficient is 0.58 at an angle of 103 degrees in polar form. Okay, then after that we have found the value of the input impedance, the normalized input impedance, which is 0.36 minus J 0.6 ohm, and we have also found the value of the angle of the reflection coefficient seen at the input end, which is 246 degrees or minus 114 degrees. You can use any of these two values. One thing to notice is that the magnitude of the reflection coefficient does not change. Why? Because the constant reflection coefficient circle remains the same. Therefore, using this, you can write the reflection coefficient seen from the input end is 0.58 at an angle of 246 degrees in polar form. Okay, now this input impedance, since this is a normalized input impedance, you can denormalize it by multiplying it with the characteristic impedance of the transmission line. So Zin is nothing but Zin multiplied with Z0, which is 36 minus J 60 ohm. Alright, so the key takeaway is first, that if you know how to locate ZL, the normalized load impedance in Smith chart, then you can find VSWR circle, the mod of the load impedance, the angle of the load impedance, the input impedance, the return loss, and the angle of the reflection coefficient, provided you know the value of the length of the transmission line, which was given in the question as 0.3 lambda, because without this you cannot find Zin and you cannot find the angle of the reflection coefficient seen at the input end. Okay, so I hope this problem will help you to solve an intermediate level question which is usually asked in a GATE exam or in any engineering level semester exams. Okay, if you have any doubts regarding this question, please write in the comment box. I will be happy to help you. In the next lecture, I will try to solve another problem on Smith chart which will help you to increase your knowledge in the Smith chart problems. Thank you for watching this lecture.